Good morning. Did you hear me? Okay. Morning, everybody. Uh, so I'm going to start with something that I left over in parabolic equations, and then Pablo is going to continue. And I'm going to present also the lab for parabolics, and then Pablo is going to continue with shock waves. Um, so remember we were solving the heat equation here. And we wanted to numerically we want to solve it. So we have a for Dirichlet boundary values. We have a scheme, okay? So in that scheme we were solving this equation here. We were solving this, but we have to put penalties, right? Because this one doesn't implement the boundary conditions properly. So we implement some boundary conditions and some operators, second order operators, that were built this form, like here, where M is a positive matrix, symmetric, and this approach in such a way, this is built in such a way that this is the approach, the second derivative, the finite difference that converges to the second derivative to some precision, depending on the and so here is with the penalties, we get this equation where we penalize the last point. This E0 here is a matrix that has a 1 here and then is 0. So this is just the first value, and so this is the vector, remember, that has a 1 here and 0 all over the place. So this is just the first point. This says that this says dt of b0 equal to d2b at 0 minus h 1 0 0 gl times b0, okay, and the other is the same for the other, and this h minus 1 0 0 is some 1 over h if the scalar product is diagonal, is 1 over h 0 0 dx, okay, where this is some number and this is the resolution. This is some number independent of. So for instance, for a second order equation, a second finite difference with second order precision, this is just 2 over, because this is 1/2. So this is a scheme. And if you do the energy equality, you get this, but you have these terms here, which are pretty bad. We don't control this, because this term has a, for instance, these ones have a b1, a b0, and then we have a bn minus 1, bn. These two are okay, these are the boundary terms. These two we don't control. So I was trying several things. And nevertheless, if you do this, the method is is stable. We run it in class, have to in the lab. You will see that it's very good. It's very stable for all values, all positive values of sigma. So the question is what is going on? Why is it stable? So I was trying to do that, thinking, and I told you that in the continuum we know how to do this. So what I did then is analyze the see where I have it here. Here I have all the calculations. So we have this problem, the continuum, with these boundary conditions, non-homogeneous boundary conditions, Dirichlet boundary. So what we do in this case is the following: you define a new variable called twiddle, which is u minus some g twiddle, and g twiddle is some extension. If you are here in your region and you have a boundary value here and a boundary here, you extend it. For instance, you just can extend by a one dimension just by a straight line. Okay, it's very smooth. Or if you are in more dimension, you have to be a bit careful. But if the boundary is smooth, you can extend this function with something. So from the, for instance, gr and gl here, you extend with a constant. Okay, connecting these 2 points, and this you call g twiddle. So now you do the equation for g twiddle. You do this. You put the equation, compute what it is, and of course here you get this minus this minus this plus this, and so now you substitute this is the equation, so this is rho, and you have these 2 terms, which you call you just leave it like this, and the whole thing you call rho twiddle. Okay, so you have you transform the boundary problem into a source, and now the boundary at the initial data, what you twiddle is just f plus the extension at equal to 0. Okay. For instance, in this case, that we just take a constant extension is just the value. Okay. So notice that for this one-dimensional problem, this is 0 because we can extend for a line, and the Laplacian of a line is 0. And this is 0 because we can extend the constant. If we are taking these 2 things to be constant in time, you could take them to vary in time. And here there will be a factor. But the nice thing here is that because of this definition, trivially this u twiddle has 0 boundary condition. And what happens if the boundary condition is 0, then the boundary term is no longer there. Okay, the energy inequality. So for this problem, for the twiddle problem, we put the same equation, right? But now we are going to put the penalties. So this is the equation, and we add the penalty. This is a penalty, but with g equal to 0. Okay. So and g twiddle now numerically will be this. So it's the rho we had minus the time derivative of g twiddle in the grid, and plus twice the finite difference of g. So this approach the Laplacian. So it's okay. So we do the calculation for the energy. what we get after taking the derivative inside is just the usual thing, the second derivatives from here, and from here you get this term. So it's the same term, but with a 2. The h goes away because here there is an h, and sigma L and this thing. Okay? So remember, these are just a 1 top 0 matrix, and this is one that matrix that has a 1 the lower corner 0. So this you transform into these terms. This is an identity by the matrix 2. Sorry, long. No, it's okay. Up to here. So this piece here, color, this in here becomes this thing, identical to that. And here you have the penalty. But notice, this term is negative, so it's negative definite, or non-positive, I would say. So we can put it on the other side, or can throw it away and put a larger equal. And this term here, the second term, this one, is 0. Why is 0? Because B-twiddle in the boundary is 0. Okay? We are imposing this boundary condition. So this thing here is 0. So this is 0. So in the energy estimate, I get this. Okay? So I control this. So in this sense, this is what gives the stability. And notice that this thing here is positive for all GL, GR positive. Okay? So that's why one gets stability. So this is stable. So what about the initial system? Well, if you look at this equation and rewrite it in terms of B, so you get this equation. You rewrite it in terms of B. You just redo the calculation we did before. So we just take the B-twiddle is this, etc. When you redo it, you get that this equation is the same as this equation. Okay, so it's the same equation as before with the source, the initial source, and here you have B minus G-twiddle. Okay, so since the other was stable, this is stable also. Okay, so it's okay. So we get the stability this way. I mean, improving this, when I say this is 0, since we are putting the penalties, this is not exactly 0, but this goes to 0 very fast. And so this thing doesn't bother. One can check this. I'm not doing this. So that's why we get stability. So let me now tell you something else. Here in this notebook, I added a 2D case, okay? And I want to discuss a bit about this. But first, let me give you where to download this, just in case you want to load it. I'll put it in the chat. So I put in the chat if you want to download it. So I did a two-dimensional case. So I just took a square, and in this square I put a Dirichlet boundary condition and evolving time. So now we are looking at solutions in some region like this. And so I want to indicate how one does it. It's pretty trivial from the one-dimensional case. So I'll do it for you indeed. So first you define the size of the box. I put 1 here. I put the number of grid points. Here I put a 50 and a 60. Didn't put 50-50 because then you can do multiplications in the wrong way and you will not discover which one you are doing. So I put different ones. You can then put the same, but I want to check that everything worked for the different sizes. So I put different here. So this is the the x, the y. There are these things here. and I create the operators, right? So the second derivative operator in the direction y, first order. So I create this the usual way, like if there were one dimension. And I get the grids here, the x and y grid. So for instance, I can create Arnold. I can create the initial conditions. So I will put this initial condition. Initially 0 here. And I have a sign one direction 5 pi and the other direction. So this is a way of seeing the. And here I put the boundary conditions. So in the boundaries I put a function. Now I have the square here. This is the 0, 1, 1, 1, 1. So I put the GL, which is the left, or the x goes, y goes, but y is top. So left is this side. I put here something that grows like 1. Here I put something that this. Here I put. So the solution will start being 0 here and will jump, become something like that. The stable solution is a solution that doesn't depend on time, so it has Laplacian equal. So it's a mixture of a constant plus something in the x direction plus something in the y direction plus something in the xy direction. So we are going to solve this. So I have the so we have already the boundary conditions, the initial conditions. And now we have to find the function, right? The right hand side of the. So remember, we are going to do something e of b equals to d2 x b, plus dy b, and then there are boundary terms. Have a b minus l over the x here, b l 0, etc. But now this condition is on the whole line. This is the line x equal to 0. So we have to sum over y here. And here we have to sum over y and x. And in the other boundary condition, you have to sum the y equal. So this translates into the following. You get this here is the multiplication operator. First you do it in the, first you put the du equal to 0. So there is nothing here. This du is the derivative, the evaluation of the right hand side. So you put a 0 here, then you multiply this for every j is in the y direction, 1 and n. For this you do the multiplication, this operator by this vector. Now the point, the b, now is a matrix, because the points I and the point j. I goes into the, so now we have a grid like this. So B is a matrix because it has points, has values here. So this is the x, this is the y. So when we put these 2 points, is that we are taking this, we are fixing the x, right? We are fixing this. So we take one of them and multiply this by the dx for every y. And here we have two numbers, because this is the constant here that goes into the multiplication here, which is 1. And this one is, I could put 0 here, it's the same. Is the value to the values of d, I put the value I have already. So this multiplication is putting du equals to. Hello? d2x y x only plus 1 by dt. But since this is 0, it just doesn't do anything. I could take it away. In fact, I think it should be better. So then we put the boundary conditions along for each j, which is a y, okay, so the y goes up. So for each y, we take boundary conditions here, okay. And then we repeat for the So this minus equal here means that is this the value that this has minus this value, and so you don't lose the values. And here we do the same for the y, for the x, sorry. So the multiplications are in the columns here, and we put the values at the end. And here is important the one. Here is important the one because I want to sum to these values of du the values that I already had here. That's why I put a 1 here. So this is that's all. There's something here which I do these views here. Somebody asked that the other day, yesterday. The views here are because otherwise, since we are taking these columns of the metric only, we don't put the view this operation doesn't do, because it takes this to be something different than the matrix du, put the values there, but then forget about the values. So when we put view, we say, okay, these are part of this du. Just act as where the metric itself. That's more or less. So that's why we need a view here. Here or no, because there is no slicing here. There is no double dot. So these are okay. These ones were the. This one have to be careful because you notice here I have problem with this thing all the time. I have problems. So what I did is to put the du's to 0 and put in the equation is 0 here, the initial data, and then I look at what I got to see whether this was okay or not. So I was playing with it. And in the original version, I used this reshape because there. Let me explain because sometimes you will see this. I say the values are in a matrix because corresponds to grid points. So naturally the vector u is a matrix. U is a metric of points, right? But I can look at it as a vector, so I could flatten it. There is a command vec of u that transform this into a vector. So put all the arrows or column one along the other to create a vector. I don't remember which way it goes. I think it goes I think it takes this one, then add this, like this. If you take the transpose, then you will, so you can change it. So this is, so I was using this vector as the variable and then do a reshape. A reshape is like the inverse operation of vector. So it takes the vector and creates a method. But this is not necessary because the grader knows that if you are taking a vector, a matrix takes like a problem. So this. So this is the right hand side. This is checking that I have the vectors. Okay. Now we set the parameters for the time integration. Take t equal to 0.5 time span dt. Remember, look at the dt is very small. Okay. Because remember for a parabolic equation, the dt has to go like 1 over delta x square. So be careful with this. So it has to be very small. Otherwise, you will get immediately problems. The code integration will complain, give you an error, and you just start trying with very slow, very small DT all the time. Then you can raise once things are working. So for instance, here I print dt over dx squared is 0.12, and this you say here it could be like minus 2 for the theoretical value if you were using the derivative, but because these differential operators, the second order, etc., we are using, they sometimes they have big eigenvectors, eigenvalues, so this is okay. You put say 0.4 or something, 0.5 doesn't work. So just keep it. So you put the parameters here. Notice the parameters, I put all the information, all the n's, the dx, everything that, and so create a problem, then solve it. Okay, I can solve it with the 6, 5 or Euler. Simply with Euler works okay. I put this adaptive false so I can keep the dt in control. Otherwise, sometimes they want to use, the method wants to use a delta t bigger because they think equation is nice, and then I put that adaptive false. And here I try some things also. Look at, I put save every step false. So sometimes you don't want to save everything, just for instance, some points on this iteration, how many steps it does. Here it has to be big sometimes, you have to put, because the dt is very small. Here for this case is no problem, but if you are taking more points, space dimension, you have to take a lot of. So you run it, and you get the solution. So you see the solution, the final, where is one here, and so it's this solution that has an x and a y constant, x times y. So you can look at the solution also in and I put some cross sections of the middle, how it goes from one side to the other. Both directions, and we can make animation of it. Is pay attention to the first point because it goes very fast to the stationary. Now it's going to start again. Very quickly, all the waves went away, and you have this quasi-stationary solution. Tension already, and half of the time is already settled. I put some reference here, the summation by power operators library, and there are 2 reviews about summation by parts and some papers. So you want, if you are interested in more about the operators, etc., you can. Okay. Questions? No questions? Questions? Okay, very simple. Thanks, Carlos. Jorge. Okay, so I'll stop now and we'll continue at 10. With Pablo is going to do the shockwave. Okay, see you later.